All right. So, guys, lesson 7.3, you can look at our learning targets up here. I can take the derivative involving e to the x functions, and I can evaluate integrals involving e to the x. The link between the two ideas that we've just been working on, what we did yesterday and today, I hope is clear. Natural log of x is the inverse of e to the x. Y equals e to the x, had this shape that we see right up here, and I can highlight that very quickly. It was this. And of course, natural log of x, which we just talked about, has this other appearance, and they are inverses of each other, and we could develop derivatives involving the ideas that we had with inverses. I'm going to actually show you some other ideas that will make life easier still. But e is about 2.71828 and so forth. Look, as we said, because we've got inverses, the natural log of e to the x, of course, is just an x. And e to the natural log of x is just an x as well. That's as long as x is properly defined to be positive. But look at this. E to the p times e to the q is equal to e to the p plus q. Here's just some algebra that you very well want to hold on to. That's coming right from the exponents chapter in Algebra 1, where you have x to the p times x to the q is equal to x to the p plus q. X in this case is just the number e. And likewise, we could say if we had e to the p divided by e to the q, that's where, of course, we're going to get e to the p minus q. Powers to powers are more powerful. Right here, you can see we'd get e to the pr. But now look at this. This thing right here is so amazing. The derivative of e to the x is e to the x. Whoa. And if that sounds shocking, it should be.
Wait, what? How?
How? You think, how in the world can you take the derivative of some function and get the function itself? I think a lot of kids will... Well, you'd be able to say for any x value, the slope would be equal to e to the x. Now, you can look at that and say, I don't know, is that even possible that that's true? Here's a proof, because I know this can seem so unbelievable. Look, let's just say I've got y equals e to the x, and I'd like to take the derivative. Now, of course, right now you'd say, well, taking the derivative, my word, I'd be using the theorem to do that. I can't use a theorem if I'm trying to prove it. But I'm going to take a log. Yes, I heard Sean just say take the log on both sides. In fact, take the natural log on both sides. And what is the natural log of e to the x? It's just x, isn't it? Right? And then you'd have this. Now, if I gave you natural log of y equals x, I could take the derivative of that. So let's do that right now. We're going to say take the derivative. Now we're going to have to take the derivative implicitly, aren't we? What's the derivative of natural log of y? 1 over y, dy dx, chain rule. What's the derivative of x? 1 with respect to x. Oh, so dy dx is equal to y. What was y? Oh my goodness. Oh my word. Wow. We've just shown that when you take the derivative of e to the x, you get e to the x. Yes?
Why couldn't we do like y equals x?
Wait 1 second. Okay, jumping over here, here's a more general theorem that we definitely want to know. If you're taking the derivative of e to the u, where u is a function of x, you'll get e to the u times the derivative of that function. That's the chain rule. That's the chain rule, right? So if you know that, and this is the most important thing for you to know, because now we can go ahead and start doing some problems here. We can do like example 1, we can do example 2. Let's take a look at example 1. Take the derivative of e to the cosine of 2x. Guess what we're going to get? E to the cosine of 2x. But now you're going to say, well, you got to take a derivative of that function up there in the power. So my next question to you then is, what's the derivative of cosine of 2x? Negative sine of 2x. Ooh, you got to do a chain rule within the chain rule.
2
times a 2. Everybody okay with that? So, how do you write it at the end? You're going to say, well, I've got a negative and I got a 2. You might want to bring the sine of 2x out in front too. You don't have to. Then you'll have e to the cosine of 2x. And that's what you got. Okay? Okay? We doing all right? Okay, now look at example 2. At example 2, guys, I can tell you already, this is such great review. You can't just take the derivative in one simple step. You're going to have to use the product rule, right? And that's really what you're going to continue to see in this chapter. You can say, well, I've got my original function, that's my u. Now I've got to take the derivative of e to the negative x squared. What's the derivative of e to the negative x squared? E to the negative x squared, chain rule, negative 2x. You got to take the derivative of that inside part here, right? That's the chain rule. I'm not done. That's my uv prime, right? Now what? Now I'm going to have u prime. What's the derivative of x with respect to x? 1. And then I've got my v. That's e to the negative x squared. So cleaning it up a little bit, we can say out in front we'll have negative 2x squared e to the negative x squared plus e to the negative x squared, and you are done. Okay? We doing okay with that? All right. Take a look at the back. It's not the longest lesson today, but as you're looking here, you could say, now wait a minute. If what we just saw was one of the most simplest derivatives you could ever have, of course, chain rules can make anything more complicated. But if you were to just have the integral of e to the u du, you'd say, well, the antiderivative of e to the u is e to the u itself. Then you got to say plus a constant. But of course, as we take a look at, say, example number 3, you might guess what method we're going to go to repeatedly. Use substitutions. And that's by the way, why we write e to the u du. What do you think we're going to let u equal in this problem? Well, how about 1 over x? And kids will say, why? Well, because I'd like to get something. Remember, use substitutions in general are reversing the chain rule, right? And I'm going to try to say, well, a chain rule deals with that composition. So, and it would definitely help you out if you could see it e to the u. Now, I hope you remember, what's the derivative of 1 over x? Negative 1 over x squared, right? And then dx, like if you're going to multiply by the opposite reciprocal here, you'd say dx is a negative x squared du. So here's my integral of e to the u, and my dx becomes a negative x squared du. And I hope you can see very quickly that the x squareds are going to cancel out, and you're going to be left there with that negative 1, and you can bring that negative 1 out in front. Okay, so I'm going to do that. Having trouble with the pen here. So I'll have a negative 1 e to the u du. What's the antiderivative of e to the u? E to the u. Don't forget you get a constant there. Would that be my final answer? No. You got to say, now this u here is really going to be 1 over x. And that's going to be your final answer. If you're feeling nervous, take the derivative and double check that you're right. Okay? Okay, for example 4. Wow, we're having some trouble with the screen here. There we go. Let's let u, what do you think we're going to let u equal here? Negative 4x. du is negative 4 dx, and dx is du over negative 4. And at this point, I do want to point out that your bounds are x values. You're saying, look, if x is equal to a 1, and of course we're looking at this right here, guess what you would have to equal? -4. And if x was equal to 3, why am I getting that? That's your upper bound. Guess what you would equal? -12. So this integral, the 1 becomes a -4, your upper bound is -12. I'll have e to the u, and my dx is du all over -4. Well, now, look at this. I could definitely factor out a -1/4. And at this point, if it's bothering you to see the boundaries written this way, and I know it does bother kids sometimes, change the negative out in front to a positive so that then the upper bound really is the larger of the two numbers. You don't have to do that. Your integral works out the same whether you do that or not. But what's the antiderivative of e to the u? It's e to the u. And then I'm going to evaluate that between -4 and -12. And that's going to be e to the -4 minus e to the -12. And even right here, this would be your final answer. Okay, you could take reciprocals of it. This would be sufficient. Okay, one more. And this is so important to talk about solving a differential equation. Guys, solving a differential equation is super, super, super important. We're going to see down the road that when it comes to points given to free response questions, differential equations very often would be the greatest amount of points given. So I'm going to show you how you can do this real fast. We'll have dy dx is equal to 4e to the 2x plus 3e to the -2x. And they're effectively saying, can you find y? When they say solve a differential equation, they're saying find out what y is. We're going to tell you what y prime is, but we want you to find y. And they're also going to give you something called an initial condition. So here's how you do that. You could separate variables. That's very important. You're going to see the College Board refer to that repeatedly. Notice I just multiplied both sides by dx. And guess what you do next? We're going to integrate. Now, what's the antiderivative of 1 with respect to y? It would be just a y. And kids will say, shouldn't you put a constant in? You could, but we're going to link our constants only on the right-hand side. Now, here, I'm going to take an antiderivative. And this is where you could do use substitutions, but I'd like to show you a shortcut. Look, this is what I'm getting at. We know that normally if I had that in an integral, I'd let u equal 2x. Would we all agree with that? Now, by the way, if you're just really on your toes, and if you're thinking through this, you'd say, well, normally I just saw if I took a derivative of e to the 2x, here's a little hint for you to help you out. If I took a derivative of e to the 2x, I'd get e to the 2x, and then I'd have the chain rule. I'd have to take the derivative of the inside, wouldn't I? How about, rather than doing the u substitution, we just very quickly say, I just need to reverse the chain rule. We're going to divide. Yes, good. We'll say, I know this antiderivative would be e to the 2x, but rather than multiply by a chain rule, I'm going to have to divide by that chain rule constant. Now, the big question is, are you sure that you did that right? Check it by a derivative. You see what I'm getting at? You'd say, what's the derivative of e to the 2x? We just saw that up here, up on the top right side. We'd say it's e to the 2x times 2. And so you could see the 2's would cancel out. Now we're going to